Say 6 players enter a tournament. Everyone plays everyone else exactly once, and every game has a winner. No draws. We'll record each result with an arrow, pointing from the winner to the loser. Now look at the mess that comes out. Often, there's no clear champion. This player beat that one, who beat this one, who beat the player we started with. A loop, with nobody on top. So here's the surprising part. Even in that mess, you can always line all the players up in a single row, so that each player in the row beat the next. One unbroken chain of wins running through everybody. It feels like the chaos should make that impossible. It never does. Such a line always exists, and by the end, you'll see exactly why. So here's the exact claim, stated carefully. In any tournament, you can always list the players in some order where the first beats the second beats the third, and so on, all the way down. One order threading through everyone, always following the arrows forward. Now, we could try to be clever and build that order all at once. We won't. The one idea in this whole video is smaller and much stronger. Don't build the line, grow it by one. If you can already arrange everyone but a single player, I'll show you the last one can always be slipped into the right spot. Do that again and again, and the line builds itself. First, let's pin down that word. Tournament. Forget sports for a second and picture a round robin. Every pair of players meets exactly once, and every game has a winner. No draws. We draw each result as a single arrow, pointing from the winner to the loser. And that's the whole definition. A set of players, and between every pair, one arrow. Count the games, and you're just choosing pairs from your players. N times n minus 1 over 2. Now hold on to one small fact, because the entire proof will lean on it. Between any two players, there is exactly one arrow. One direction. Never both, never neither. So, can we always find that line? Let's try the obvious thing, and watch it fail. The tempting move is to start from the top. Find the strongest player and build outward from them. But in a tournament, there might be no strongest player. Remember the loop. A beats B beats C beats A. Whoever you crown, somebody beat them. So a greedy line stalls. You get a chain going, then hit a player who breaks it, with people still stranded outside. The lesson isn't that it's impossible, it's that starting from scratch is the wrong plan. So let's change the question. Suppose we already had a line, for everyone but a single player. Could we always fit that last person in? Here's the plan, and it's a classic. We'll show the line exists for one player. Then we prove that whenever it works for some number of players, it has to work for one more. Put those together, and it works for every size. That's induction. Start tiny. One player, all alone, already is a line of length 1. Now the real work. Suppose we've got a line for some group of players, each beating the next. And in walks one new player, drawn in pink, who hasn't been placed. The entire theorem now comes down to a single question. Where does the pink player go? Let's just try to place them, starting at the front. Compare the newcomer with the very first player in the line. Maybe the newcomer beats them. If so, we're done in one move. Put the pink player at the front, their arrow running into the old leader, and the whole line shifts over to make room. A longer line, and every arrow still points forward. If the front didn't work, try the other end. Compare the newcomer with the last player in the line. Maybe that last player beats them. Then it's just as easy. Hang the pink player off the back, arrow coming in, and again the line grows by 1. 2 easy escapes. But what if both of them fail? The newcomer loses to the front and beats the back. This is the heart of it. The newcomer loses to the front, and beats the back. So as we walk along the line from left to right, somewhere the story has to flip. From players who beat the newcomer to players the newcomer beats. So find the last player in the line who still beats the pink newcomer. Call them the pivot. And here's the magic. Because the pivot is the last one to beat the newcomer, the very next player does not beat them. And remember our one small fact? Between two players, there's exactly one arrow. Not beaten means the newcomer wins. So the pivot beats the newcomer beats the next player, and the pink player drops in right between them. Both arrows forward. There is always a gap that fits. Step back and look at what we just proved. Whatever the newcomer's results, one of three things is always true. They beat the front, or the back beats them, or there's a pivot in the middle to drop past. One of these always fires. So a line for any group of players can always take in one more. And that is the whole ladder. One player is a line. Add a second, a third, a fourth, each newcomer snapping into place, the line never breaking, all the way up to every player in the tournament. However the arrows fell, the line is there. Before we celebrate, let's poke it. Take the smallest interesting tournament. 3 players in a perfect loop. Rock, paper, scissors. There's no best one, no honest ranking. Whoever you pick, someone beats them. And still a line exists. 3 of them, in fact. Any of the 3 can start, and the loop hands you a valid line. So be careful what the theorem is actually saying. A line where each beats the next is not a ranking. It crowns nobody. And here's a small bonus that quietly guarantees the whole thing. Count all such lines in any tournament, and the total always comes out odd. An odd number can't be 0, so a line can never fail to be there. Now the other direction. Which hypothesis is actually doing the work? Our one small fact was that every pair plays. What if we drop it? Erase a single game, so 2 players never met, leaving a gap where an arrow should be. Suddenly a player can be cut off. No way in, no way out on the side you need. The line can't reach them, and it breaks. So this isn't magic that works for any pile of arrows. It needs the tournament to be complete, every pair decided. Take that away, and the guarantee is gone. Time to name what we built. A line through all the players, each beating the next, is called a Hamiltonian path, a path that visits everyone exactly once. And the fact that every tournament has one is known as Rédei's theorem. But the name worth keeping isn't Rédei's, it's the move. We never constructed the answer directly. We assumed it for one size smaller and showed we could always extend by 1, grow it by 1. That single idea proves things exist across every size at once, and it reaches far past tournaments. So where does this go next? Our 1 has 2 loose ends, a first player and a last. Now, suppose the tournament is knit together tightly, so that by following arrows you can get from anyone to anyone. Then something lovely happens. The line can be bent around until the last player also beats the first, closing it into a loop. A single cycle through everyone. That's a genuinely stronger statement, and it is true, but the reason is a story for another day. For now, a question. When can a winning line be bent into a winning loop? If you'd like more single theorem stories like this one, subscribe. And drop your answer to that last question in the comments. When does the line become a loop? The clearest one gets pinned.